Okay, so now we're going to learn how to find the necessary information for solids of revolution created by rotating around a vertical axis. So like the one in the example here, if we were to rotate this region around the y-axis, we would have washers that were horizontally oriented, like so, instead of ones that were kind of vertically oriented when we were rotating around the x-axis. So that's going to change things a little bit. But we're going to have to find the same necessary information, just things will be slightly different. So let's go ahead and see what we need to know. First, we need to know the lower bound again, but instead of it being the lowest x value contained in the region, we are going to be looking for the lowest y value contained in the region. And that is because before, we had these washers stacked up along the x-axis. The stack was growing this way. Well, now our stack of washers will be growing up along a vertical axis. So that's why we will be, our bounds will go along the y-axis, which means we're going to have to write our functions in terms of y, or meaning that we're going to have to get them in the form of x equals something in terms of y, because we'll be integrating with respect to the y-axis to find our volumes when we get to that point. So for the lower bound, we're looking for the lowest y value contained in the region. Upper bound, we're looking for the highest y value contained in the region. Once again, we're just looking for, where does this thing stop on the y-axis? So we want to find the greatest y value that's contained in the region. We're still going to need to know the radius of the outside of the circle. We'll still denote it big R. It's still going to be the distance from the outside of the region to the axis of revolution. But instead of measuring it vertically, we're going to be measuring it horizontally because it's a distance from a vertical axis. So these, once again, these functions are going to have to be written in terms of y to be able to set up for integration later. That's the one big change. And then the radius of the inside circle will still denote little r. It'll still be the distance from the inside of the region to the axis of revolution. But once again, we'll be measuring it horizontally, which means we're going to have to write our functions in terms of y to actually find out what those values are. So let's look at an example. We're going to take this region bounded by the graph of y equals negative x plus 2 and y equals 0. And we're going to rotate it around the y-axis, or the line x equals 0. So let's get an idea of what that looks like. So you see, as I start to rotate this around the y-axis, we get this cone shape. So we're going to find the necessary information for that. First thing we're going to know is the lower bound. So remember, for the lower bound, we're looking for the lowest y value in the region, and that's going to be y equals 0. So our lower bound will be 0. Our region doesn't go any lower than y equals 0. Our upper bound is going to be the greatest y value contained in the region. So that's going to be y equals 2, because our region doesn't go past 2 on the y-axis. We're going to find the radius of the outside circle. Remember, we're measuring it this way. So the outside function is y equals negative x plus 2, but we're going to want to write it in terms of y, get it in x equals form so that we can integrate with respect to the y-axis. So we're going to solve this function for x. So I'm going to add x to the side. It's going to be x plus y equals 2. So x equals 2 minus y. No matter where I put this line, the height or the width of this strip, or the radius of this thing that we would rotate, is always going to be negative x plus 2, or 2 minus y. So that's going to be the radius of our outside of our circle. We'll still keep it big R, and it will equal 2 minus y. Lastly, we want the radius of the inside of the circle. Well, just like in the one we did before, now our axis of revolution is actually attached to the shaded region, meaning that the distance between it and the inside of the region is 0, because they are the same line. We'll still denote it little r, and it's going to be r equals 0. So let's look at another one. So we have the graph. This is y equals x squared, and up here we have y equals 4. And now for the first time we're going to rotate it around a different line other than a coordinate axis. We're going to rotate this thing around the line x equals 2. So before we go further, let's take a look at what that looks like. It'll look a little different. So we hit play. You see that as this thing rotates around that axis, it kind of looks like an angel food cake almost. So that's the thing that we're going to be finding the volume of later. So find our necessary information. This is still y equals 4. This is still y equals x squared. We're going to look for the lower bound. So what's the lowest y value contained in the region? Well, the region doesn't go any lower than y equals 0, so our lower bound is 0. The upper bound of the region, the greatest y value contained in the region. So the region stops right here, and that y value is 4, so our upper bound will be 4. Next, we're going to take the radius of the outside of the circle. Now this is where things change a little bit because we're measuring from this line to the outside. So here's our x revolution going out to the outside or the furthest away from the region, which would be right here. And once again, we need this in terms of y. So if I take y equals x squared and I solve for x to get it in terms of y, I take the square root of both sides. I get x equals plus or minus the square root of y. So I actually get two different functions. And what happens is this side, or the side on the positive side of things, that's going to be x equals the square root of y, because that's where we have, we're on the positive side where our x values are positive. And over here on this side is going to be the negative part of that. So that's going to be where we have x equals negative square root y. That kind of just looks like a tail on the square root. So that's negative square root y on that side. So if we're measuring the distance from the axis of revolution to the outside of the shaded region, it's this purple line here, which is going to be x equals negative square root y. So the question is, how do we get the distance from here all the way out to here? Well, remember, we want distance to always be positive. You know, if you were going to Wilmington, you wouldn't say, when you're going to Wilmington, it's 120 miles. When you come back, you wouldn't say you want a negative 120 miles. It'd be, you know, just 120. So since we want distance to be positive all the time, we're going to subtract the rightmost value, rightmost function, minus the leftmost function. So since our axis of revolution is further to the right than the outside of the shaded region, our axis of revolution is going to come first in our subtraction. So this is going to be big R equals 2 minus, and that would be the outside function, which is going to be negative square root of y. So it's going to be 2 plus the square root of y. And then for our radius of our inside of our circle, we're going from the axis of revolution to the inside part of the function. So this is our little r. That part up here was our big R. So little r is the distance from the axis of revolution to the function that is closest to the axis of revolution. So here's our little r. Find that distance. We're going to take the rightmost function, which is in this case is the axis of revolution. So 2 minus, and then we have this green part here, which is the function x equals the square root of y. So 2 minus square root y is going to be our little r, and I'll squeeze it in here. Little r equals 2 minus the square root of y. So that one's a little bit different, but you know, if you keep in mind you're still looking for the distance between the axis of revolution and the outside for the big R, and the axis of revolution to the inside, or the closest function for little r, just keep that in mind. You should be able to keep it straight. But go ahead, you got 3 practice problems, so give those a shot, and then we will take this necessary information and start to evaluate the integrals to find the volumes.